Introduction. Data engineering is a field that revolves around the design, construction, and maintenance of systems and architecture that enable the collection, storage, and processing of large volumes of data. As a data engineer, understanding how data is distributed across nodes is crucial, as it directly impacts scalability, efficiency, and reliability. This essay explores various aspects of distributed data systems, focusing on the role of virtual machines, external hard drives, and techniques like horizontal partitioning and data aggregation. Distributed systems and nodes. Data distribution across nodes is fundamental to distributed systems. These nodes can be internal components within a platform like Hadoop or external entities such as virtual machines and external hard drives. Hadoop is a well-known example of a distributed storage and processing system, but there are numerous others like Cassandra, Spanner, and DynamoDB, each with its unique approach to data distribution. Virtual machines and external hard drives as nodes. Virtual machines, VMs, and external hard drives are commonly used as nodes in distributed systems, particularly by cloud providers offering scalable storage solutions. The primary advantage of utilizing VMs and external hard drives lies in scalability. As storage and processing demands increase, new nodes can be seamlessly integrated into the system, enhancing its capacity to handle larger workloads. Moreover, these nodes contribute to high availability, ensuring that if one node fails, the system can fail over to another node, maintaining uninterrupted operation. Horizontal partitioning, sharding. Horizontal partitioning, also known as sharding, is a technique employed to distribute data across multiple nodes or servers within a database. Sharding involves splitting a database into smaller, more manageable pieces called shards. These shards are then distributed across various nodes, allowing for efficient data retrieval and management. The key advantage of sharding is scalability. By distributing data across multiple nodes, the system can easily accommodate increased storage and processing demands. This approach ensures that as data volume grows, the system can expand horizontally, maintaining performance and efficiency. Data aggregation. Data aggregation is another critical technique in distributed systems. It involves collecting data from multiple sources and combining it into a single, summarized dataset. This process simplifies the analysis of large data volumes, making it easier to identify patterns and trends. Techniques in data aggregation. Data aggregation can be performed using several methods, including MapReduce algorithms and distributed SQL queries. MapReduce algorithms break down data into smaller chunks, process them in parallel, and then combine the results. Distributed SQL queries allow users to query data stored across multiple nodes in a distributed system. It is essential to note that data aggregation typically relies on simple mathematical operations such as summation and averaging rather than complex linear algebra or matrix multiplication. While linear algebra and matrix multiplication are prevalent in fields like machine learning and computer vision, most data aggregation tasks focus on straightforward mathematical transformations. Transforming raw data. Data aggregation systems play a pivotal role in transforming raw data. They take raw data from various sources, often in diverse formats and structures, and convert it into a more summarized and organized form. This transformation is crucial for making data more accessible and usable for analysis, enabling organizations to derive meaningful insights from their data. Data transformation and pre-processing. Introduction. The process of data transformation is an essential step in data engineering. It involves cleaning and pre-processing raw data to ensure it is suitable for aggregation and analysis. This essay will explore the various steps involved in data transformation, the distinction between database instances and database accessors, and draw parallels to object-oriented programming in Python. Data cleaning and pre-processing. Data transformation typically starts with cleaning and pre-processing the raw data. This involves standardizing the data and correcting any errors or inconsistencies. Key steps include removing outliers, identifying and excluding data points that significantly deviate from the norm, filling missing values, replacing missing or null values with appropriate substitutes, Converting data formats, ensuring all data conforms to a common format or structure. These pre-processing steps are critical as they prepare the data for subsequent stages of aggregation and analysis. Parsing. The process of cleaning and pre-processing data before aggregation is often referred to as parsing. Parsing involves extracting relevant information from raw data and converting it into a structured format, such as JSON or XML. This step is crucial as it ensures the data is in a suitable form for aggregation and analysis. Database instances and accessors. A clear understanding of database instances and accessors is important for efficient data management. Database instances. A database instance refers to a single, running instance of a database system, such as MySQL or MongoDB. It encompasses all the tables, indexes, and data stored within the database. Essentially, it is the active environment where data operations are performed. Database accessors. A database accessor is a software component or tool that facilitates interaction with a database instance. Examples include SQL clients, ORM libraries, and NoSQL drivers. These accessors enable querying, updating, and manipulating the data stored in the database instance. The analogy to a cloud instance is apt, just as a cloud instance provides access to a virtual machine or server in the cloud. A database accessor provides access to a database instance. Object-oriented programming in Python. The concepts of database instances and accessors can be compared to object-oriented programming, OOP, in Python. Classes and objects. In OOP, a class serves as a blueprint for creating objects. An instance of a class is an object that represents a particular entity within a program. This object has its own state, attributes, and behavior, methods. Comparison to database records. In some ways, creating an instance of a class in Python is analogous to creating a database record or row. An object encapsulates data relevant to a specific aspect of a program, such as user information or the state of a game. However, the analogy is partial. Complexity and functionality. Python objects can encapsulate far more complexity and functionality than simple database records. Interactions. Objects interact with each other in complex ways through methods and attributes. Dynamic nature. Python objects are created and deleted dynamically at runtime, whereas database records are managed explicitly through SQL queries. Conclusion. Data transformation and pre-processing are crucial steps in ensuring data quality for aggregation and analysis. Understanding the distinction between database instances and accessors enhances effective data management. While there are parallels between OOP and Python and database management systems, each serves unique purposes within their respective domains. Recognizing these similarities and differences allows for more effective application of data engineering principles in various contexts. Database management systems and Hadoop. Introduction. Database management systems, DBMS, and platforms like Hadoop play crucial roles in handling and processing large volumes of data. This essay explores the concepts of database instances, the architecture of Hadoop, and the roles of NameNode and DataNode in a Hadoop cluster. Additionally, it discusses the similarities and differences between cloud authentication mechanisms and Hadoop's file system components. Database management systems. In a database management system such as MySQL or SQL Server, a running instance of the database stores all the data and allows users to perform queries and other operations through SQL, structured query language. This instance serves as the core of the DBMS, providing an interface for data manipulation and retrieval. Hadoop, an off-the-shelf solution. Hadoop is a powerful platform designed for distributed storage and processing of large datasets. When integrated with a DBMS, Hadoop offers a scalable and flexible architecture for managing and analyzing vast amounts of data. Hadoop clusters and nodes. In a Hadoop cluster, data is distributed across multiple nodes, which can be physical machines, virtual machines, or a combination of both. Each node runs a component of the Hadoop framework, such as a NameNode or DataNode, working collectively to manage and process the data stored in the cluster. The actual data stored on each node is organized into blocks, which are contiguous pieces of data located on a single device, such as an internal or external hard drive. Runtime and dynamic components. Hadoop clusters are typically designed to run continuously over long periods, as starting up a cluster can be time-consuming and resource-intensive. However, individual nodes can be added or removed dynamically to accommodate changes in data volume or processing workload, offering flexibility in managing resources. Namenode and datanode in Hadoop. The namenode and datanode are critical components of the Hadoop file system, HDFS, each playing complementary roles in managing and storing data. Namenode. The namenode serves as the central component of HDFS, maintaining metadata about the files in the system, including the mapping of blocks to datanodes and the File System Access Control List, ACL. The namenode acts as a file system catalog, tracking what data is stored where in the cluster. Importantly, the namenode does not store any actual data itself. Datanode. The datanode is responsible for storing the actual data blocks in the cluster. Each datanode holds a portion of the data and communicates with client applications to read and write data as needed. Unlike the namenode, datanodes do not maintain metadata about the files. They rely on the namenode to provide this information to clients. Cloud instances and authorization. In cloud environments, such as Google Cloud, creating an instance often involves setting up authorization between accounts to access files within the cloud instance. This process typically involves generating a token, which serves as an authorization key to access cloud resources. Comparison: Cloud authentication and Hadoop's HDFS. While there are similarities between cloud authentication mechanisms and Hadoop's HDFS components, there are also significant differences. Similarities. Metadata management. The namenode in Hadoop and tokens in cloud authentication both serve as mechanisms to manage access to resources. The namenode maintains metadata about data locations, while tokens authenticate and authorize users. Access control. Both systems use specialized methods to control access to resources, ensuring secure and efficient data management. Differences. Specific roles. The namenode and datanode roles are specific to the Hadoop architecture, focusing on distributed data management within HDFS. In contrast, tokens are part of a broader security mechanism in cloud environments, used for authenticating and authorizing users across various cloud services. Functionality scope. The namenode and datanode are integral to the storage and retrieval process within HDFS, whereas tokens primarily handle user authentication and access control. Distributed systems and data processing, key-value pairs, MapReduce, and database management. Introduction. Distributed systems and data processing have become essential in managing and analyzing vast amounts of data. Key concepts such as key-value pairs, MapReduce, and database management systems like MySQL and Oracle play pivotal roles in these processes. This essay delves into the significance of key-value pairs in distributed environments, the functioning of MapReduce, and compares the features of MySQL and Oracle. Additionally, it explores how concepts from these systems enhance performance, scalability, and fault tolerance. Key-value pairs in distributed systems. A token in a distributed system can be viewed as a type of key-value pair. The key serves as a unique identifier or label, while the value contains the associated data or information. In the context of key-value pairs in MapReduce, the key might represent something like a document ID, and the value could be the entire document or a specific field. Tokens ensure the uniqueness of key-value pairs in distributed environments like Hadoop and provide a secure and consistent mechanism for authentication and authorization. MapReduce. Processing and transforming data. MapReduce is a programming model used to process and transform large amounts of data in a distributed manner. Each key-value pair represents a single piece of data, and each piece is processed by a different mapper node. The map function is applied to the key-value pair to generate intermediate key-value pairs. These intermediate pairs are then sorted and passed to the reducer nodes, where the reduce function processes them further. This approach allows for efficient and scalable processing of large datasets across many nodes in a Hadoop cluster. Authentication tokens in distributed systems. Authentication tokens do not typically hold meaningful data themselves. Instead, they act as unique identifiers used to authenticate a user or an application and grant access to a system or resource. The actual data is stored separately and accessed through the authenticating key or token. Some tokens may include additional information, such as expiry time or access privileges, but their primary purpose is authentication. Database management systems, MySQL and Oracle. MySQL and Oracle are both relational database management systems, RDBMS, that use tables to store data and adhere to the ACID, atomicity, consistency, isolation, durability principles. Despite these similarities, there are several key differences between the two. Database engines. One major difference lies in the type of database engine they use. MySQL traditionally uses the MyISAM storage engine, whereas Oracle uses the more advanced InnoDB engine. InnoDB supports transactions, foreign keys, and better performance and scalability, which are essential for modern database applications. Oracle's redo log and buffer cache. Oracle's architecture includes components such as the redo log and buffer cache, which enhance database performance and ensure data durability and consistency. The redo log continuously records changes made to the database, allowing recovery from failures or crashes. The buffer cache stores recently used data in memory, enabling quick access to frequently accessed data. These mechanisms are similar to the principles behind key-value pairs in MapReduce, where data is split and processed efficiently to improve performance and scalability. Splitting data and handling noise. In distributed systems, data is split into smaller pieces for processing, which can introduce errors or distortions. Data splitting is managed by partitioning algorithms that use techniques like hash functions, range partitioning, and manual partitioning. These algorithms aim to minimize information loss and ensure each partition contains a representative subset of the data. Challenges of data splitting. Splitting data unevenly can lead to issues such as data skew, where some splits contain more data than others. This imbalance causes some nodes to become overwhelmed while others remain underutilized. Uneven data distribution creates inefficiencies and performance problems, similar to a large amount of data being forced through a narrow pipe, causing fragmentation and less smooth data flow. Distributed systems and data processing, concepts and models. Introduction. Distributed systems and data processing are fundamental to managing and analyzing vast amounts of data efficiently. Key concepts such as the MapReduce programming model, load balancing, database management systems, DBMS, like Oracle, and different data models play crucial roles in these processes. This essay explores the MapReduce model, the importance of load balancing, the functionalities of Oracle's background processes, and the various database models used in static and dynamic databases. MapReduce programming model. Overview. MapReduce is a programming model designed for processing large datasets in parallel across a distributed computing cluster. It utilizes various algorithms to split and partition the data, including hash functions, range partitioning, and manual partitioning. These algorithms determine how the data will be divided among the nodes in the cluster, ensuring each node handles a roughly even share of the data. This balance maximizes the efficiency of the MapReduce job as a whole. Load balancing. Load balancing is a technique used to distribute incoming network or computing workloads evenly across multiple resources, such as servers or databases. In a MapReduce cluster, load balancing ensures that each node processes an approximately equal amount of work. This prevents any single node from becoming overloaded, allowing the cluster to process the workload more efficiently. Load balancing mechanisms include hash-based routing and round-robin scheduling. Flexibility and customization. The MapReduce programming model is flexible and adaptable to various workloads and data types. The specific partitioning methods used can vary depending on the application's needs and the dataset. Different partitioning methods, such as hash partitioning or range partitioning, may be employed to ensure efficient processing. Custom partitioning algorithms can also be implemented to achieve desired results, balancing speed and accuracy.